Whew. Top of the evening, top of the afternoon, top of the morning, whenever you're watching this video. What's happening to all your aunties and uncles, nieces and nephews, brothers and sisters, mothers and fathers. I'm back with another video, guys, and this time this video is going to be covering some model preparation and data preparation. So I believe the last video that I recorded, if I'm not mistaken, was doing some more data analysis on Spotify data, which is going to be the video previous in this playlist. So this file right here and this video right here is going to be going over some of the data pre-processing we had to do for models and model tuning, and I'm gonna keep it 80 with you guys. I'm gonna keep it a G with you guys. This took a while to run. It took me almost 3 days of just figuring out which was the fastest and how to let it run. All right, so let's just start. Let's just go ahead and get into it. So obviously right here, import all your packages you're gonna need at the beginning of the file. And we have my working data frame, which is gonna be from the pickle file that I merged from the last file in the last video that we went over. So that's that. And then the data prep. So basically what I had to do is load this label encoder, which I will explain in a minute. And then what I did is I went ahead and I got all the numerical features that I'm going to be using to predict which genre the song falls under. So as you can see, it got categories: year, top genre, beats per minute, energy, dance, decibel levels, liveliness, valence. I want to say this is duration, acoustics, speechiness, and then I want to say this is popularity. So these are all the numerical features, right? All numerical features. But as you can see, well, almost all the numerical features, but as you can see, top genre right here, it still says hip hop, Atlanta hip hop. It's not a number. So basically that's what this label encoder comes in for. This label encoder goes in and basically essentially assigns each of these genres. So hip hop, ATL hip hop, Chicago rap, Boston hip hop, supplies one of these with a number. It's a 1-to-1 mapping. So that means each genre gets a number. So as you can see down here, hip hop in the data frame is now 43. Atlanta hip hop is 4. Chicago rap is 20. New Jersey rap is 52. ATL trap is 5. So each genre has a different number, and that is needed for most models because most models take in numerical features and cake in numerical features, except for a few kind of like if you're doing like a natural language processing model, obviously that takes in words in a sense. But the reason how you type in a model and you'll see sometimes by like machine learning applications is that you type in a word and it prints back out a word. How does the model work? Well, behind the scenes, you type in the word then gets coded into numbers, or in this case different classes. The model does whatever the model is coded to do, and it spits back out a number. But before you see the final I guess answer or the final product, it gets converted back into a word. So for example, let's just say I typed in this row right here to get the genre. So I typed in 2012, 80, 77, etc., etc. What it would do is take in those features and it would do whatever calculation it needs to do, and then the model would print out a number. So the model would print out 43, but you as the user, you don't know what 43 is because you normally don't see this part. This is kind of like the back end part. You don't see this part. So what would happen is it would go through a decoder, quote unquote, and 43 obviously in this label map is equal to hip hop, so you would see hip hop. So that's how the label encoding and decoding works, and how you're able to see words when you actually input something instead of numbers, which is numbers is what you see on the back end. Through the decoder, words is what you see on the front end. So that's what the label encoder does. And as you can see, obviously transform that top genre column into numbers. And then obviously I like to see a correlation matrix just to see if any of these are even remotely related to each other. I'm gonna be honest with you. So obviously, one is super high correlation, and then blue is super cold correlation. So obviously, it's gonna be a 1-1-1 diagonal across this matrix. And then as far as the variables that are most correlated with each other, valence and energy, dance and pop, beats per minute and speechiness. So I mean, and it's not really high correlation. I say no higher than 0.4, which is a 40% correlation, which means none of these variables really have anything to do with each other, which can be both good and bad, because you do want some similarity between your variables, because the way the model trains, you want some similarity, because if none of your features have any similarities, then there's no point in training that model. So you do want to have some similarities. So basically here, I'm taking out the X, taking out the top genre, because the top genre is what we want to predict. The top genre is our Y. It's our classification. And the Y is going to be the top genre column, and the X is going to be everything but the top genre column. So that's why I'm splitting into X and Y, and then I'm calling train test split to test it. Test size is 0.3, which is good. I guess is good enough. And then from this, from the train and the, I guess you could quote unquote test, it's called temp here, but test, I'm doing validation as well, which is about half of the test size. So what happens is that you take the data frame, you split it, 70% goes to training, 30% goes to test. And then from the test, half of that is validation, which is used to make sure the model doesn't overfit and everything goes well behind the scenes with training. And then the test is the actual test data that you test your model on. So validation is kind of like the test data, but not really. It's kind of like if there was a 3-tiered layer. So if it was, so it would be test. Wow, that's not what it'd be test data, validation data, and then train data. So it would train the model, then validate, then test. So that's how it would go if it was a 3-tier system. So you can see the X train, the X val, X test, Y train, Y val, Y test. And the Y is going to be this is going to be series, because it's no longer a data frame. It's just taking the values of one column, which Python automatically and NumPy automatically turns to a series. So that's what they're doing. And here I'm just doing it as an array, because further down what was happening is that since I'm running 2 different models on the same Python file, it kind of got confused, and that's a normal thing to do. It's not like anything was wrong, but in the same Jupyter file, sometimes they can get confused when you call Xtrain for one model, try and manipulate it, and then call Xtrain for another model. Sometimes they can get a little confused. So I just made it Xtrain log, and log does not stand for log base. Does not stand for log base 10, log base 2. It just stands for logistic regression model, which is the first model I'm going to run and train. So for the model, I just called, your basic function, logistic regression. Max iteration is 1,000. I always like to do max iterations of 1,000. I also probably will not be able to run that many more iterations because of this machine that I'm on and the way my Jupyter Notebook is set up. So as you can see, we have a convergence warning. So basically how a logistic model works is that it trains, it fits the data, and at some point it's supposed to converge. At some point you're supposed to find the lowest, minimize the loss function. So the lowest amount. So let's say like you have a, let me see. Let's say you have, okay, yeah. All right, so boom. Let's say this path is what the logistic model does. So basically it goes back and forth, trying to minimize the loss function, which is the point of most functions, actually all functions. So it goes back and forth. At some point, it's supposed to reach this lowest point, and this would be the model. This would be where the model would stop, because the loss had been minimized completely, and this is where it's supposed to be the most accurate while minimizing the loss. However, we get this warning. This warning says convergence failed, or model failed to converge essentially. So basically it failed to reach this point. So that means the model did not reach this point at all. This can be because of one of two reasons. Either, obviously in this case, my number of iterations wasn't big enough, or is that your data is so sparse, there's no correlation with any of the features, that your model just simply cannot converge. So in this case, it is a number of iterations, which I knew it was going to happen because this took forever to run, and I simply was just tired of waiting for it to run. I'm gonna be honest with you. If I had a more powerful computer and set up my Jupyter notebook differently, I probably could have run like maybe 2,000 iterations, and maybe that would have converged. But the accuracy is going to be a little bit lower, as you'll see, because I only chose 1,000 iterations. So obviously fit my model, and I did a predictions based on the X test. I was on the X test, and then I got the predictions, which is just an array, so it's going to spit out. Obviously, these predictions are the mod or top genre. So like 63, 428, those all map to things that we saw in this dictionary, this label map earlier. So we get that, and then the accuracy is 40%. I'm going to be honest. Given the amount of data that I have, which is about 22,000 rows of data, nearly 40% on the first go without tuning is not bad. I'm not going to lie. It's really not that bad. And you can see on the train set, 40, on the test set, a little bit less. But around 40%, not that bad. I know I'm being generous. I know some other data scientists will be like, oh, no, that's horrible. But honestly, for what I'm working with and for what tools I have at my disposal, 40% is not bad, but I know we can do better. So basically what these lines are doing right here, these ones are basically, so they're getting one row from the test, one row from the test logic, or one row from the test split of my main data set. So this is just one row in X test log, which I created up here. So this is one row of X test log. So what it's doing, these are all the features that it gives, all the features, all the numerical features. So we're going to use a predict, and this is going to predict the probability of what genre it is. So the text prediction, so what the logistic model does is it gives out a list of probabilities. So of the classes, because there's 67 classes, it's going to give the percentage of what class it could be. It could be class 43, it could be class 67, it could be class 5. So let me explain that a little bit better. So if we go up here, the logistic model is going to spit out, okay, there's a 37% chance it's class 43, which is hip hop. There's a 26% chance that it's ATL hip hop. It's a 5% chance that it's Chicago rap. So that's what it goes. So it goes through each of these classes and it assigns a certain percentage. So basically what this is doing here is I'm taking this row and it's going to give me, you know, all the percentages of all the classes. So there's 67. So it's going to be a lot of percentages, but I'm looking for the main one, the max one. So the class that has the highest percentage is Detroit hip hop, which is class 28. And that percentage that the logistic model has it at is at 33%. So in other words, there is a 33.5% chance that whatever song this is, given these feature models, there's a 38%. You have a 38% chance that it's going to be Detroit hip hop. That's not that high, but given 67 classes, I would say that's pretty high. I'd say that's pretty high. Now, tuning parameters. This is gonna be yeah. Let me hold on. I gotta respond to these few texts real quick. Brief intermission, people. Give me a second. So basically what model tuning parameters is that each model has a hyperparameter. And so what this function is doing, what I'll explain in a second, is basically just taking the parameters and just tuning it. So give me like 2 seconds. All right, so basically what this function does is okay. So basically, this function right here, model hyperparameter tuning. I already explained what hyperparameters are. Basically, what this is this function, if I'm remembering right. So these are different solvers. So each logistic regression has a bunch of different solvers, which I can explain in another video because it's going to take me way too long to explain in this video. I want to keep it around less than 30 minutes. So basically what this is doing is that this is using different classifiers, different solvers, and it's basically just training the test and the train, and it's giving the highest accuracy. So whichever one has the highest accuracy is going to be first and second and third and fourth. So here, so this is going to go 0, 1, 2, 3. So this is 0, this is 1, this is 2, this is 3. So after all this, the train accuracy, test accuracy, precision, and recall, the model that does the best is the first one, which is the Newton CG solver. The max iterations is 500. I had to cut it down because this would have taken, if I did 1,000 iteration, it quite literally would have taken 45 minutes to run, and I did not have that kind of time, at least right now. So this gives a 46% accuracy, which is getting closer to 50, which given this data set and given the features, that's a good, I'll take that. That's a good, over 45% is good. And so that's what this does. So this is just the solvers. There's no penalty. There's no trying to minimize the L2 loss function, no trying to minimize L2, none of that. That's where this one comes in. L2 penalty basically combats overfitting. So there might have been some overfitting in these models. This model tends to fight that overfitting to make it more accurate. And as you can see, it's pretty much the same. Like, I don't think anything changes. Maybe, yeah, I don't think anything changes in the top one. So I'm deducing that top model is probably going to be the best one. It's probably going to be the best it can get, that top model. You can see some slight improvements in these other three models between, I'm comparing this one and this one. Obviously you can see 0.42 is the same. There's a little slight increase, but this top model is going to be the top model. And then I had to stop this because this is just, you can see keyboard interrupt. This was taking just way too long, and I need to record this. But the C element basically is the trust factor. So I want to say that the lower the number the least you trust? Let me see. Let me look it up real quick. I looked these up, but I just can't remember. Hold on a second. Did I search this up? Okay, so sorry. Yeah, C, essentially, there is a lot of mathematical terms involved, talking about give weight to the training data and a lower to the complexity penalty. Essentially, what C means is that a high C value is trust this data a lot. A low C value says that this data is not going to be representative. It's not representative. So after adding the C component, if it's telling you to make a certain hyperparameter super big or super small, to not trust it, because you shouldn't trust the data. So essentially, I have it 0.001 because I'm saying this data might not be fully representative of real world data, which it isn't because it's my data. If I was doing it based off of my data, I'd probably set the C to maybe, I don't know, 0.8 or 0.9. I could probably run that. Probably just have to set aside maybe like an hour for it to run, and then I could, after I do this whole process. But for now, just so I can have something to run and something to show, I'm gonna set it at 0.01 because I don't really trust the data a lot. And this one I did set a max iteration is equal to 1,000. I probably will cut it down to 500 because this is 500, this is 1,000, but as you see, the accuracy does not change. So I think it's going to take a lot, and I mean a lot, more iterations for it to converge. Is basically what I'm doing at that. So now, the final model that I'm running on this page, I do have one more model I want to show you guys, but that, currently working on that. It's something I'm not really that an expertise in, or I haven't had a lot of use of. It's natural language processing, but we will get to that in another video. Right now, we're going to talk about XGBoost. Now, if you guys stick with me, and if I do stick with this YouTube channel for a while, you guys are going to learn the fact that I absolutely love XGBoost. It is powerful. It is accurate. You can do so many things with it. You can do multinomial classification, binary classification. You can do natural language processing. I love XGBoost. I really do. If I could do every single project that I've done with XGBoost, I will 100% do it. So as you can see, did the same thing, multi-softmax. So this is multinomial multi-class classification. So it's going to give percentages just like logistic. I want to say, let me make sure before I spout this. Multi-softmax. Yep, it does the same thing as logistics for me. It assigns probabilities to each class. So as you can see, did the same thing that I did in terms of train data and test data and fitting and all that stuff, same as logistic. But as you can see, the accuracy is at 94%, and you can see why I like XGBoost the most, because it is powerful. You can do a lot of things with it, and even without any hyperparameter training, whoops, logistics behind in terms of accuracy. I mean, it's not even close. Like, I like to use logistic regression and base regression just because it's a base, but I just use it as a base, as a comparison to see, you know, how much better English, man. Sheesh. How much higher the accuracy you can get between models. So I could have stopped right here because 0.94 is super high and super accurate. However, we're data scientists here. We're machine learning experts here, or we're trying to be. And after you do one base model, you always have to tune your parameters. So basically what this is, and this took a minute to run, let me tell you, man. This is called grid search. So basically what it is, it takes these max depths, learning rate, and subsample, and it combines these, and I mean it combines each one, and it runs the model, and whichever one spits out the highest accuracy, that's the parameters you use for your model. And when I mean every combination, I mean every combination. So it'll go 3.1.5, 3.1.7, 3.1.1, and it'll do that. And it took about 45 minutes to run. So the grid search, obviously I have my model, have my parameter grid, have my cross validation. I set it to 2 because if I set it to 5, it was just going to take too long. The problem with a lot of these model parameters, I don't know why on this file, I don't know why in this project. Maybe it's because it's my first big project. These things, and my data set's so big, it takes a while. It took 45 minutes for this grid search optimization to run, and it took 45 minutes just for this block alone took 45 minutes, and this block alone took 45 minutes. So yeah, it just takes a while, guys. I thought I was doing something wrong. I really, really did. I thought something was gonna crash, but no, it just takes a while. So you can see, obviously it's training, and the best set of hyperparameters is at learning rates 0.1, max depth to 7, subsamples 1, and it gives an accuracy of nearly 98%. You really can't get much better. You really cannot get better than that. So if this was a production project, I'm stopping here. 98%, you quite literally cannot get that much higher. In fact, this is unrealistic because most models and most real data, they don't get this accurate. If they did, the world would be a lot better and run a lot smoother, trust me. So the last thing I want to talk about in this video, so there's grid search optimization, which takes, different combinations. And then there is random search. Oh man. Random search, quite literally, it is what it sounds. It is a random. You take a random max depth, you do one of the learning rates, hold on. If you guys hear me typing, it's just clearly because I'm looking these up. Oh yeah, it does. A uniform van, right? So it takes a random one of these, and a uniform continuous random variable. Uniform random variable. I'll explain all these math concepts later, but right now I just want to get the code out and get your minds thinking, because this takes a uniform, and this also takes a uniform, takes a random. Obviously, same model. Obviously, for this, for some reason, this runs faster than this. Maybe it's because it's not doing all the combinations, doing a random one, and because the model accuracy is already so freaking high. Yeah, so I could actually set the cross-validation to 5. I could set the number of iterations to 10 because this, and I knew that random search was going to be the quickest, which is why I saved it for last. So we does a random search, it fits it, get the best parameters, learning rate 0.10, max depth 6, number of estimators 175, subsample 0.9, and we get an accuracy of 98%. So this is 99% accuracy. And you can see why I stopped here, because I'm not going to try to push, because it's gonna, if I'm trying to get 100% accuracy, where is the goddamn, come on now, bro. Wow, okay, well, if we're trying to push to 100, this is what's gonna happen. The model is gonna go like this. Closer we get to 100, it's gonna create an asymptote line, which is never gonna equal 100. So that's why I stopped here, because this is essentially at 99%, 98.6%. That's 99%, which is why I stopped here. So that means that of all the models that I ran, all the hyperparameter tuning, all the intricate math behind these models, the best model out of Logistic and XGBoost for this data set, given the features, is going to be this model right here, this XGBoost model with these parameters right here. When that means, if we go all the way back up to wrap it all together, if we give that model with those parameters, these features, or these features right here, there is a 99% chance that it will guess the right genre, which, given the amount of data set, is about right because it's just numerical data, right? But what about song titles? Can I create a model that can get me the right genre based on the song title? Because a lot of songs and a lot of genres have a lot of the same words. So can I create a natural language processing model that can give me, I'll take even a 50% accuracy rate, that can correctly predict the right genre? Who knows? I'm going to find out. And when I do, I'll record it and you guys can find out too. I'll see you guys in my next video. Peace.